Hello, Thailand. I wish I could be with you this week, but that was not to be. What I want to talk about is really the issues related to climate change and how energy storage can help solve some of those problems. The Nobel Committee stated that we had laid the foundation of a wireless fossil fuel-free society. But it's now up to all of us to actually move to the next step and take action to make sure it happens. As we all know, our climate has been messed up in the last 10 years or so, and I show you some examples just from the last 18 months on all three continents, Europe, Asia, and Americas. From floods, tornadoes, glaciers melting, fires, everything has gone wild. So what has happened in the last 20, 30 years, and particularly since the beginning of this century, we have gone at least two disruptions. The first one is the communications revolution that was enabled by the lithium battery. And you all now can get instant communication from around the world. This wasn't the case 30 years ago. And in the last 3 years, we've had disruptions from COVID, and COVID showed us the challenges of the global supply chains, but it also showed us just how fast we as scientists can come up with solutions and the remarkably fast vaccines and successful vaccines that the scientists came up with. Now we all have to adapt to climate change. We can control it, but I don't think we can roll it back. We just have to make sure it doesn't get too much worse. Clearly, we have to do with much less fossil fuels. We need cleaner, renewable electrical energy in the future. And we in New York State are particularly proud that we do not generate a single kilowatt hour of electricity from coal today. But for an electric-based economy, we need clean electricity. Beyond hydro, solar and wind will dominate, but they are intermittent, so storage is critical. And lithium batteries are the dominant form of portable storage today. They're going to be a dominant form of grid storage tomorrow. So let's look at where we started out 50 years ago. ESSO had the initiative to get into renewable energy. They were into fuel cells, batteries, solar cells, and were very interested in electric vehicles. And we embarked on a battery program, and I'll show you two of the batteries we made at that time. This small paperweight we gave away to potential customers. This one was built in the mid-1970s, and it's still working. Below that is larger batteries, 6 inches by 4 inches by about an inch thick, that were used at the EV show in Chicago in 1977. And those were the largest rechargeable lithium batteries at that time. In the center, I show you the original patent and myself a few decades ago. And I want to emphasize, we used in those days single crystals, and the field is coming back to single crystals. So if you want to see some of these small cells, they now reside in the Nobel Museum in Stockholm, together with one of the sales brochures that Exxon, or more strictly Exxon Enterprises, which held the renewable energy components of Exxon. So from those small cells I showed you, this is where we are in transportation today, from small two-seater vehicles. This is one in Bermuda that my wife and I rented, to large trucks, 16-wheelers or garbage trucks, both very effective. They can use electric power. Beneath that, I show you two buses. The Mercedes bus has a solid-state battery in it, and the BAE Systems bus has a standard liquid electrolyte battery in it. And the BAE bus comes from our neighborhood here in Binghamton. And here is a Raymond forklift truck an industrial grade one, again using lithium-ion batteries. And beneath that is a electric vehicle, a BMW vehicle. If we didn't have any supply chain issues today, we'd be selling probably 2 to 3 times as many electric vehicles as are presently on the market. And this gives you an actual trend of the sales of electric vehicles. It's growing exponentially. And I say it would grow even faster if we had the batteries available. As I noted, electricity from renewable energy needs storage. Today in the United States, renewable energy is lower cost than new coal. So there's essentially no new coal going into operation, but lots of wind and solar. As I've already mentioned, it's intermittent, so needs storage. And here are 3 storage facilities. I show you 3 in the United States. The large one in the bottom center here is in Moss Landing, California. That's about 1.5 hours south of San Francisco. It takes the excess solar energy generated during the daytime and stores it for use during the rest of the day. And it is, in fact, not big enough to take all the excess solar. And this is, even though it's 1.6 gigawatt hours in size, that's 4 times the size of any other battery storage system in the world. This is particularly effective there because inside an original gas power plant, so all the grid infrastructure is already in place. On the right-hand side of the bottom is a small facility in Binghamton. This was placed next to a coal power plant about 2010. Within it being operational for about 1 month, the coal power plant was turned off and never turned on again. Above that is a lithium battery farm that smooths the energy from those wind turbines and shifts the power for up to about 8 hours. So these systems are making money today. They're very effective. But let me just touch on a few items about the lithium battery so you can all understand some of the challenges. Today, all of you have lithium-ion batteries in your devices. Since they should not contain any lithium metal, because if they do, then you'll get these dendrites formed, as Russ Chianelli took this optical picture back in the 1970s. As you plate out lithium, dendrites form, they go through the separator and short out the battery, then you get the fires as Avastor and AT&T found. So there are essentially no lithium metal batteries on the market today. Just for those of you who are not familiar with batteries, let me just show you a typical setup of battery. Every battery is the same. It has an anode, which is in this case where the lithium resides when it's charged, a cathode where the lithium goes on discharge, and in between we have an electrolyte, and the lithium ions flow through the electrolyte and the electrons flow through the external work and do, so the external circuit and do work. So all these are based on what we call intercalation chemistry. This is where we intercalate guest species, in this case, these lithium ions into a host lattice. Here I show you graphite, and on this side, it's a layered oxide or a layered sulfide. So the structure of these host materials does not change, except for maybe a slight expansion. So your ions can go in and out thousands of times without destroying the structure. And this is what we mean by an intercalation material. So that's the basics. The 3 of us who won the Nobel Prize did different things to make that happen. It could not have been done by any one of us. So we have myself there with John Goodenough and Akira Yoshino 3 years ago in Stockholm. So let's go through a little bit of the history so we can see where we come from and where we need to go. So at SO, we started out with pure lithium metal. We saw those dendrites. So we used aluminum, and aluminum forms a 1-to-1 alloy. This works fairly well for 10 or 20 recharges, but then it crumbles. Akira Yoshino then developed the idea of using graphitic carbons, and that's what is now used in the anode. And these have been used effectively commercially since about 1990. But the challenge here, you need 72 grams of carbon to store 7 grams of lithium, and the carbon takes up half the volume of the cell. So the carbon has to go if we're going to increase the energy density. So people are looking now at replacing the carbon with tin or silicon. Tin or silicon both react with more than 4 lithium ions. So their capacity is the same basically as lithium metal. But our goal eventually is to get back to lithium metal. On the cathode side, we start out with this layered compound, titanium disulfide. I show you this is the structure here. This works very well. It's a metallic conductor. So that in an electrochemical reaction, you've got to move electrons in and out, as well as lithium ions in and out. So this worked exceptionally well. The voltage, however, was only about 2.5 volts. John Goodenough, who was working on the magnetic behavior of lithium cobalt oxide at that time, recognized the similarity of the structures and tested this in an electrochemical cell and showed that lithium cobalt oxide worked. And this is now what's in most of your small devices. But cobalt is expensive. It comes from the Congo, and a lot of child labor is involved. So there's a big push to remove the cobalt out. So most of these layered oxides now contain nickel, manganese, as well as cobalt, or in the case of Tesla, contain nickel and aluminum with the cobalt. But our goal is eventually to get all the cobalt out. John Goodenough also came up with these lithium iron phosphates. These are more stable materials, which I'll get into in a moment, but they store much less energy. But they contain no expensive cobalt, no expensive nickel, so there's a big push there to make them work for grid storage. We and my lab were looking at solving this energy storage drop by inserting 2 lithiums into these phosphates. And to do that, we need a transition metal that can go from, say, 5+ to 3+, just as vanadium does. So just to emphasize, there's still a huge opportunity to increase the energy density of commercial batteries. So that'll make the batteries lower cost, make your cars drive further, and make grid storage smaller. So if you look at those percentage numbers in that red oval, that is the percentage of the theoretical volumetric energy density that is actually in commercial cells today. So you can see the best value there is 25%. On the weight basis, which is this last column here, it's also about 25%. So there's a huge opportunity to actually increase that energy density. And we have a major program with the Department of Energy here to increase that to 50%. To do that, we've got to get most of the carbon out. We've got to get more lithium in, and we need materials with higher ionic and electronic conductivities so we can make the electrodes thicker. So what we're doing in this DOE project, this is called Battery 500, is to increase that energy density from 250 to 500 watt-hours per kilogram. These materials, I said, they're layered materials are shown on the right here. These are the layered oxides. This is lithium ions. And they're commercialized in this meatball morphology. So the primary particles are 1 to 100, 200 nanometers. The secondary particles are about 10 microns across. And this makes very good packing. To increase the energy density, we've taken out the graphite anode. We're using pure lithium metal. We're now using an ether-based electrolyte. What we found in the first 5 years of this project, we can increase the lifetime, increase the energy density, and by increasing energy density, we keep the cost coming down. So you can just see at the bottom here's the number of cycles we got out. Vertical axis is the cell energy density. And you can see from year 1, we got 50 cycles. Year 2, over 250. That's at 300 watt-hours per kilogram. The following year, we went up 350. And today, we're about 800 cycles at 350 watt-hours per kilogram. And the leader of this project is Jay Xiao, one of my ex-PhD students who are now at Pacific Northwest National Lab. And we work with these pouch cells. So we're making great progress. We're optimistic we can get to at least 400 and maybe 500 watt-hours per kilogram. I mentioned earlier at Exxon, we started out with these single crystals. So I'll show you on the top left here. These are, several millimeters in the plane, so very large. SUNY wanted large single crystals of lithium cobalt oxide to make it very safe. The higher the surface area, the more reactive the material is. So you want to reduce the surface area. But to get the power of the batteries up, there's been a tendency of late to go with smaller particles. And this is one where the 622 refers to 60% nickel, 20% cobalt, 20% manganese. In the last year or two, there's been a feeling we should go back to single crystals, and I'll show you a picture here from Jeff Don, where we got 50% nickel, and the single crystal is about 3 micron. Why do we want single crystals? We've got less surface area, which means we've got less side reactions, so we get a much longer life. In principle, this could allow million-plus mile batteries. Clearly, none of us are going to drive 1,000,000 miles, but what this will allow is for your electric vehicles to be attached to the grid at all times when the vehicle is not actually moving. This will make the grid more resilient. It'll let you power your home if you lose power, but critically to the user, the grid will pay for part of the cost of your battery in your car, so reduce the cost to you of your electric vehicle. So there's a big push to make these batteries last 20, 25 years. So why can't we do this faster? What's slowing us down? And the issue really is this global supply chain is untenable. We learned this during COVID. We couldn't get mass. You've got semiconductor issues. It's just too constrained today. This raises security issues, and it particularly raises sustainability issues. So we scientists have to find ways of eliminating the critical elements or locally source them. So there's a huge effort to reduce the amount of cobalt going into batteries. Recently, the United States opened a mine in Idaho, but because we have no processing facilities here, this ore is then sent to Brazil and Finland for processing. Similarly, the nickel and the graphite, we should be sourcing them locally. So I want to give you an example of particularly what we are doing. North America has been and continues to be a hotbed for battery activities. The universities are leading the world in intellectual property of the chemistry in the batteries. We have a lot of investment in startup companies to push the frontiers, come up with new concepts. But regrettably, there's a bit too much hype on those systems. But we can invent things, come up with ideas, but there's a major gap in prototyping batteries and in battery equipment. So what we have proposed is to try to make some changes there. There's extensive US federal funding, just as there is in Europe. And I'll show you one example of this, and this is Battery New York. This is an effort of ours. And in this effort, which is funded by the US federal government and by New York State, we have received $113 million to build this effort. Half of this money will go into a battery center, which will allow flexible technology and manufacturing development and allow pilot lines so ideas can be tested, developed. We can make 1,000 batteries before we put them into a gigafactory. But we can't do that without a supply chain. So we have a large effort to attract companies to the area who can supply us with every little piece you need to make a battery, including the materials themselves, the containers, the electronics, and so on. But a major impediment in both North America and in Europe is the lack of a workforce. So we're putting around about $12 million into workforce development. This is new programs and allow new folks to get into the business, from workers on the floor to management to engineers who can connect the batteries to, for example, cars, to the grid, to wind, and so on. We continue to obviously want to have new ideas. So we need startup, and that's what we mean by acceleration. We need continuous technology innovation. And what the goal of our center really is to change the technology behind making batteries, which really hasn't changed in the last 30 plus years. We want to get out the bad chemicals, so we make clean, environmentally friendly batteries. And another big aspect of our effort, our facility will be built about 4 miles from our university here in the town of Endicott. This is where IBM was founded. And about 10, 15 years ago, IBM decided to quit making computers. And there were about 10,000 people then without jobs. So what we plan to do is train those people into the battery clean energy systems so they can regrow that manufacturing center in Endicott. This facility was kicked off on October the 20th. That's just about 6 weeks ago, by Alejandra Castillo, who is the Undersecretary for the Economic Development Agency. And I'm discussing with her batteries in our small gigafactory that's already in Endicott right now. And on the right-hand side, I'm showing you Senator Schumer, who leads the US Senate, who is a champion of our effort and was also on site for the grand kickoff of this effort. So the US government is putting many billions of dollars into helping solve the climate change. A lot of this is going into batteries, some is going into hydrogen, but there's going to be a real push here, just as there has been in Europe. So what is the future for cleaner, safer energy? We need new manufacturing technologies. We've got to leapfrog the old Asian 1990s technology. Right now, it takes 50 to 60 kilowatt hours of energy to make a 1 kilowatt hour battery. We need to find new methods to have clean mining with clean energy. For example, hydro energy. We need to replace carbothermal reactions. That is where we reduce the oxides with carbon and make a lot of CO2, use electroreduction in its place. And a big push is we need clean recycling technologies. This will give us a sustainable society with clean chemistry. But to do all of this, we need regional supply chains. These need to be in Europe and North America, just as they are presently in Asia. And I want to conclude by saying, besides having a regional supply chains, each region needs to be more self-sufficient and responsible. So energy storage is just one example where globalization has gone too far. We've seen the examples in semiconductors, COVID masks. We all have to emphasize sustainability. All materials, used materials should be recycled, and they should be recycled within the region where they are used. So I want to emphasize the developed nations must be responsible for all the materials they produce, whether it's plastics, clothing, electronics. We can't ship off all our junk, as we call it, to third world countries. And then I know there's a lot of plastics right now going to Thailand, polluting the areas around Bangkok. That kind of has to stop. So the Americas have to recycle their own plastics. Europe has to do the same thing and not just put it on the boats to get rid of it. And I'll stop there. Thank you very much.